given day. Anyway, this is lecture 7, part 5, and I'm going to refine our interpretation of mass spectra by looking at the fragmentation patterns that appear and describing how they will be used to kind of piece together the molecule in a retrosynthetic fashion. But first, let's review parts 1 to 4 in a relatively straightforward, instructive manner by supplying a step-by-step interpretation guide. So our first step is to locate the highest set of peaks in the mass spectrum, namely those peaks set in the spectrum that have the highest n to z values. And we're looking at the A's and the A+1s, namely the isotopic satellites. The first thing we want to do is determine whether it's an odd or even value. And then we tabulate the lines as they appear in the data and determine which one of these, or which among them, corresponds to the A line and which apply to the, or correspond to the isotopic satellites. So in this particular case, we've identified 74 as the A peak and the 75 and 76 as the A+1. We next have to multiply if the line is not at 100% abundance, we find a scaling factor which we multiply against that 43 to become 100, and then apply that same scaling factor to the A+1 and A+2. Here I changed the table accordingly. So I've multiplied the 74 peak by, I believe it was 2.3, and the same 2.3 multiplied it by against the original abundances at 75, 76. I then supply the error, 10% or 0.2 absolute, and I come up with the data as indicated. I have not touched the 73 peak because it's not going to be part of my analysis in this particular example. I next count the number of atoms for each element by looking at the A+1 and A+2 satellite lines. So in this particular case, I want to first count the carbons. So I would divide the 5.3 by 1.1, which is the isotopic abundance per carbon, 13. And so they're additive. So dividing 5.3 by 1.1 gives me almost 5 carbons, somewhere between 4 and 5, and that's what I would assign. Similarly, oxygen, an A+2 element, has an O18 abundance of 0.2%. I divide the abundance, the A+2 line, 76, by 0.2, and I get 1. And if I incorporate the error, I can go from 0 to 2. Based on the estimates, namely the 4 or 5 carbons and 0 to 2 oxygens, I set up a truth table, as I demonstrated in the last part, and start to systematically organize the possibilities based on the numerical estimates based on the isotope lines. So I try 5 carbons and I wind up with something that doesn't work. I try 5 carbons even with an oxygen, I still don't get anything that works. I have to go to 4 carbons maximum, and I get something that starts to look plausible there. 4 carbons, 1 oxygen. And since I can't really rule out nitrogen because it's even valued, the even value aspect of it tells me I have to add nitrogens in pairs. So if I drop to 3 carbons and 2 nitrogens, which is the only way I can add 2 nitrogens, I come up with a number that gives me a negative saturation index, so that's equally rejected. So the only real possibility in this case is 4 carbons, 1 oxygen, and that gives me an empirical formula. This is a fortunate example in which I have only one plausible guess in my interpretation. When you work with larger molecules, you're going to find that you get as many as 4 or 5 guesses, empirical formulas that work at this point. And the trick will be how to refine that. number downward, and that's the role of the fragments. And then secondly, we're going to use supplementary spectroscopic data, namely NMR and IR, to further reduce and refine our interpretation. So what I'm referring to is the fragmentation. So the trivial fragmentation is just the loss of a hydrogen, namely hydrogen abstraction, which is usually characteristic of having an anomalously large line paired to the A. So sometimes this can be small, as indicated in this particular example, or it could be two peaks of roughly the same height, which would be not like any of the isotope conformations or configurations that we've described for this course. What we're primarily interested in is the regions down here, where we start to look at these molecular ions, or these ions. They're not complete molecules, they're actually fragmentary ions, and try to figure out from the changes what they are. And, you know, we have an expert here with us on breaking stuff. This is actually slander. She's actually a very good little cat, but it makes for a good story. So let's look at the fragments of this particular mass spectrum. We're always going to reference everything from the molecular ion. We're not going to look at them by themselves initially. We're just going to compare their position relative to the molecular ion. So doing that for the first peak at 59, we subtract the molecular ion 74, or subtract the 59 from the molecular ion 74, and we get 15, which looks like a methyl group. If we look at the second line now and do the same subtraction, 74 minus 45, we get 29. That looks like an ethyl group. So now we're getting somewhere. We have a couple of ideas on what kind of structural elements are part of the molecule. So I notice about this is what you should notice in general about fragments is that their M to Z values are odd valued. There'll be an exception to this when there's a nitrogen present, but keep in mind that fragments are generally odd valued. So now I want to look at some of these fragments and kind of think about them. And what I'm going to look at first is the fact, well, I have something that falls off weighing 29 AMU, namely the ethyl group. And what falls off is usually neutral, so it leaves behind an ion, and that would correspond in this case to the thing at 45. But I'd like to know if something weighing 45 falls off as a neutral species, leaving behind a 29 ion. And I do see that in the spectrum. So I see a peak at 29, and I see these things pairing up. So the two blue arrows suggest to me, on the one hand, at 45, I lose an ethyl group, and yet at 29, it looks like I have an ethyl group. So the 45 is the complement, or at least it seems that way, of the 29 peak. So what separates those two is 16 AMU, right? And that can only be an oxygen, or well, most likely it's an oxygen, given the fact that we have only 4 elements to work with in these problems. So it looks to me like the peak at 45 is an ethoxy ion. And if I look, well, I can also look at 31, which kind of looks weird. And I would guess that to be the 31, so some chemical rearrangement. So this one doesn't interest me so much as the 29 and 45 pairing. Okay, so this is the actual data obtained for that 45 peak in the previous slide. I've scaled it up to get the corrected values, so scaled up to 100 for the 45 peak. That gives me a better estimate of the A plus 1. I see that that's now 2.2 when I've done the multiplication. The A plus 2 peak has been raised to 0.9, which is a bit high, but we know that oxygen's a little weird. So I'm looking at something with probably 2 carbons and maybe an oxygen. I want to set up my truth table to test that. So I think in terms of 2 carbons and 1 oxygen, and I get a very nice result there with a saturation index of 0.5. And I want to draw your attention to the fact that when you calculate the saturation index for a fragment, you should get a fractional number. To be careful, though, I should try 3 carbons just to be safe. And I try that in my truth table, and I see that I get a number with a negative saturation index, so that's automatically rejected. I get similar problems if I try to go with 2 oxygens. So my interpretation of the 45 peak is therefore pretty reliable at this point. Okay, so I'm going to look now at another example, namely that of ethylene diamide. And this is going to be of interest to us because it has 2 nitrogens, and the molecular ion is therefore going to be even valued, and I expect it to appear at 60, namely here. And one thing I notice immediately is that that peak is very small, so that implies or tells me that the molecule is very unstable when it gets ionized and passes through the mass spec analyzer. And in fact, it breaks in half and gives me a fragment instead as the dominant species appearing at 30. And this seems to contradict what I mentioned in the previous example, namely that fragments have an odd value m to z. But here's the thing, and this is the exception, and this is also very useful in the sense of interpretation. When you have a single nitrogen in the fragment, the single nitrogen is odd. The fragment is by nature odd, so 2 odds make an even. So when you see an even valued fragment, that tells you that you have an odd number of nitrogens present. So if I now try to analyze the peak appearing at 30, I have the following information. I get an abundance of 2.2 at the A+1 position, suggesting as many as 2 carbons, and an A+2 of 0.2, suggesting some oxygen. But I realized that I can't, even though I have this possibility, namely 2 carbons and 0 to 2 oxygen atoms based on the abundances and the errors, that would not give me, any combination of carbon and oxygen would not give me an even valued fragment. Secondly, I already know, based on the fact that it is even valued, I have a nitrogen present, so I can't possibly have a nitrogen and an oxygen. I can't have more than 2 carbons. So that fragment has to be comprised of a single carbon and a single nitrogen, right? So that in turn gives me for my guesses, a 1 carbon, 1 nitrogen combination, saturation index of 0, looks good. And if I try the 2 carbon scenario, it doesn't look bad. There's nothing wrong with it. It does give me a saturation index that's reasonable. So I would probably keep that as an aside, but recognize that the combination of the isotope factors, namely the 0.4 and the 1.1, does get me up around 2. So the molecule does seem to be splitting in half. So the even valued fragment is one type of signature that you can use for helping to identify what's in the molecule. I'm going to show you now a second example using benzaldehyde as the case study. So benzaldehyde has the aromatic ring attached to an aldehyde group, and we already spoke about hydrogen abstraction giving us a large peak to the lower MZ value of the parent, namely, so in this case it would be 105 compared to the 106 line. Okay, but we're now interested in a bigger fragment, namely the whole aldehyde group coming off. So this, and that would give us a minus 29, resulting in a line appearing at 77. And this is your typical signature. When you have a substituted benzene and the substituent gets torn off during the fragmentation process, a characteristic signature peak at 77 appears, indicative of the benzene ring ion. If you have a disubstituted, it may appear at 75 or 76. So if you start to see major peaks in the vicinity of 75 to 77, you can kind of begin to suspect, anyway, the presence of an aromatic system that's been substituted. So in review, in summary of what we've just described in this part, you look at the fragments and you count or see how many AMUs separate that fragment from the molecular ion, and use that information to imagine a substituent breaking away from the molecular ion. There are two signature cases, namely an even value turning up in the fragment, which suggests that you've got an odd number of nitrogens in that fragment. And then there's the characteristic signature of the aromatic ring, in this particular case benzene. There would be another one for, say, naphthalene. But in the case of benzene, substituted benzene, you get a characteristic fragment that's 77 AMU or MZ77. So these are things you should be looking out for as you analyze a mass spectrum. So again, this is the bibliographic information for this lecture. Fragmentation tables, in other words, a complete listing of fragments, common fragments, and their AMU values are given in most textbooks. I have made a copy of one of these textbook tables, and I have set it as a PDF document that's available on the Blackboard component of this course in the information folder. And that concludes Lecture 7, Part 5.